All set?
Yep.
All right, we'll go ahead and get started. Looks like we got a small crowd, but hopefully people will trickle in. We did mention that free to come and go. It's a lot of this is meant to be hands-on testing part of playing with the tools. So welcome to our workshop on emerging technologies in structural health monitoring. I'm Scott Snelling. I'm a managing partner with Roebling Labs. I have about 20 years of experience in the bridge industry, from design, inspection, construction, and management. We're going to be talking about two main topics today: smartphone accelerometers and non-contact sensors. The smartphone accelerometers, we have two professors from Lusofona University that are going to be joining us remotely. They're Eloi Figueiredo and Unit Moldovan, and they've made a really cool app for SHM that they'll be talking about. And then for non-contact sensors, we have Mike Ciocys with RDI Technologies. He's got his non-contact sensor here. It's really a video camera with some very sophisticated software that turns every pixel into a sensor, and he'll talk about some of that, show some demos, and have an opportunity to use it and see its capabilities, which are really quite amazing. And then we'll have time. We have this room until 10, so we'll be around. Welcome to try out the smartphone apps on our model bridge and the tools later. But the sort of panel presentation should be about 45 minutes long, and then we'll have some time for Q&A and hands-on in the room after that, informal discussions and so forth. So to start off, sort of the theme of this workshop is really to explore how we might use these tools to help you better manage your bridges. We think there's some really promising and powerful tools, but how they're going to work their way into the industry, I think, is still somewhat an unanswered question. We hope to explore it today with you all. I want to start a little story from my own career inspecting bridges. I experienced a near miss while I was bridge inspecting. These are some photos actually from that day before the near miss. I was in a UB60, probably like a lot of you have been, underneath the bridge. My colleague and I, and a pin in the UB60 failed. We plummeted 20 feet into the water below. It was basically winter time. We were wearing winter clothes. We were lashed to a steel, the steel bucket, which was quickly submerging to the bottom of the channel. We managed to unclip. We were swimming in the water. It was a marine environment, and fortunately, fishermen like to fish near this bridge. The bridge was right on the border of Queens in Long Island, and this fishing boat came up, grabbed us like we were big fish, tossed us into the boat, zipped us over to the dock. We're standing there dripping wet. I'm thinking I should probably call somebody, but my phone doesn't work. My partner had just gotten out of college. It was his first time inspecting a bridge, and he says to me, "How often does this happen?" And I told him this is definitely not supposed to happen. But the point of the story is, bridge inspection's really hard. It's hard to be thorough when you're gathering information. There's safety issues. You can, for both the inspectors and the public, you clog up traffic and so forth. And I don't think structural health monitoring is going to replace bridge inspection anytime soon, but it can make bridge inspections more productive, more thorough, provide quantitative data, and thereby increase the safety of both bridge inspectors and the traveling public. Just from a high-level view, there's about 600,000 bridges in the US, highway bridges. About 7% are structurally deficient or poor condition, but only about 60 bridges, as of that data point, is from 2020. So there may be a few more now, but a tiny, tiny fraction of those have any sort of structural health monitoring system on them. Now, most structural health monitoring systems today may cost hundreds of thousands of dollars. So the sort of bridges that they go on tend to be the new construction, signature bridge, long span type bridge that are designed for a 100-year design life, and we're not going to be really worrying about those bridges for decades. Meanwhile, the bridges we're actually most concerned about most of the time go completely unmonitored. So I co-founded Roebling Labs with a vision of bringing sensors with real-time analytics to every bridge. We're a startup. We're accepted into the Boston University Build Lab, which is a startup ecosystem, received a little bit of non-dilutive funding with the goal of building tools towards achieving this vision. We think this aligns well with, we think it's inevitable that it's going to happen eventually, and we seek to be a part of it. The USDOT, in their most recent strategic plan, really talks about advancing the use of advanced sensors. So we think we're in good company with our goal. So with that, I'm going to hand it over now to Eloi, and his partner Inut, and I'm going to do a little bit of just an introduction on them. So, and Mike, maybe while I introduce Eloi, you could bring his picture up.
Got it.
So Eloi is a full professor at Lusofona University with over 110 publications on structural health monitoring, from books to book chapters, journals, and so forth. He's the coordinator for the Civil Research Group that has collaborations with several institutions in Europe, the United States, and Brazil. And then also on Eloi did his postdoc work at Los Alamos National Lab, which has been a leader in structural health monitoring for decades. So Eloi is very well credentialed, as is his partner, Inut, who's also a professor at Lusofona University and has a similarly impressive resume. So I'm going to turn it over to you guys. Eloi.
Okay, so thank you, Scott. Let me share my screen. Okay, so I believe you are already seeing my screen. Okay, so good morning, everyone. First of all, I would like to acknowledge Ionut Moldovan. It has been really important to develop this app for SHM, a smartphone application for structural health monitoring. First of all, let me tell you that bridges are just a small part of the huge network that the bridge owners and the authorities need to manage. Besides the roads and railways, and the authorities need to pay attention to their bridges. Currently, as you may know, we are using the so-called bridge management systems, and they rely a lot on visual inspection. So the goal in the last 30 years has been to develop some kind of system that can measure data in real time and give quantitative answers to the bridge owners in order to support the bridge maintenance. Is where structural health monitoring is trying to be. What is structural health monitoring? Basically, it refers to the process of implementing a strategy based on monitoring systems to measure in real time the structural response in order to identify damage at early stages. The idea is to mimic the human nervous systems where we wanted to get there. We are not still there, but we wanted to get there. In order to do so, we have tried to pose the structural health monitoring in the context of a statistical pattern recognition paradigm, which can be split into 4 stages: operation evaluation, data acquisition, feature extraction and generation, and statistical modeling for feature classification. I would like to point out the value of the data acquisition, where basically we need to collect data using sensors. And once you have the raw data from the sensors, we need to extract some kind of features that can be assimilated to the presence of damage. And once we have these features, we need to somehow to model them in order to identify the existence of damage. This is how we pose this paradigm. So in order to do so, we came up with this idea to develop an app which can be used for everyone and can follow the statistical pattern recognition paradigm. Basically, we wanted to simplify the SHM and make it available for everyone to use. This app, this version of the app, what it does, it uses the internal accelerometer to measure accelerations from our bridges, and then we can extract natural frequencies. And once we have a lot of data, then we can use a machine learning algorithm, and that machine learning algorithm will be able to detect the presence of damage when we want. What are the advantages and drawbacks? I mean, the huge advantage, but it is also a drawback, is that it takes SHM to the fingertips of engineering community. What does it mean? It means that it might be easy to use, but we need to be careful when we think that everyone can use it. Not everyone can use it. It must require some kind of training in order to make better decisions. But keep in mind, I will show you some examples where a very simple accelerometer, like a 2-error accelerometer, can really detect anomalies, and comparing it to the traditional accelerometers that normally cost like $5,000 or $10,000. So, following the same idea of the statistical pattern recognition paradigm that I just showed you, this app is split into 4 steps. The first step is what we call structural identification, where we need to define what is the structure that we are monitoring, because we may have many structures under monitoring programs at the same time. And then we move into the step number 2, which is the data acquisition. So we need to get acceleration time series from our structures, and then move to step number 3, feature extraction. As you can see, power spectrum, where we will pick those first 3 natural frequencies of interest. And then we have step number 4, where we will, for a new measurement, we might ask the app, is this new measure statistically different or similar to the ones we measured in the past? And then the app will position that observations below or above a certain threshold defined for a certain level of significance. Of course, this app relies on the server. All calculations and storage are made in the server. We realized that it was better to have this remote server in order to manage all the data and to get all the information. The app right now, it's just a friendly environment for us to use and to manage the whole system. In the server, we can do everything. Basically, we can even add data sets. Imagine that you have tons of data sets that you have collected in the past, and you wanted to use them in order to enrich your database. You can do that. Just upload the data, and then you use the app to get new data and compare this new data into the past data. Always using some kind of machine learning algorithm to understand what we have learned or what we have in the past. How to use it? First of all, just to summarize, we measure accelerations. For how long? 30 seconds, 40 seconds, 1 minute. What is the sampling frequency? Normally, or sampling rate, we have defined for 50 hertz. It could be other, but we have defined for 50 hertz. Once we have the acceleration time series, we extract the natural frequencies using the picking technique. And then we create a data set. We get tons and tons of data, and we create a data set. And we train a machine learning algorithm. And then at any time, we can get a new observation, a new sample of data, and compare it to the past. And we'll have an answer if that data set is similar or not to the past. Let's move on into applications. We have already published a paper where we have demonstrated and we have showed that the results from the app are very similar to the ones we can get from traditional accelerometers, like the ones that you may know from PCB. We have done this comparison in the lab environment, and look at we realize picking the first three natural frequencies of a still beam in the lab, we have realized differences of 0.5% comparing both systems. 0.5% in civil engineering is almost nothing. So it means that the app is able to estimate natural frequencies very similar to the ones we used to estimate with the more expensive accelerometers. We were even able, with that still beam, to test the ability of our app to detect the presence of damage. In this case, we simulate the presence of damage using different masses, positioned in different positions. The first mass is 25 grams, 50, and 100 grams. And you can see the cell phone over there in order to get all the measurements we need. We were able to create a reference data set. As you can see, those blue dots correspond to the undamaged condition. And then you can see those triangles and those triangles and diamonds you can see there are the observations related to the damaged condition. In conclusion, the app was not able to detect the damage related to the 25 grams, but was able to detect the other cases. So keep in mind, we were able to get the data, train machine learning algorithm, and then test the existence of damage. Let's move on to another bridge, to one real world bridge application, those what we call twin bridges. They are concrete bridges, pre-stressed concrete bridges located in Brazil. So once again, we have the opportunity to compare the results we get from a $2 or €2 sensor inside our cell phones with the other sensors, in this case from Ciocys, that can cost, I can tell you, that equipment you can see over there in blue, it costs roughly €10,000 or $10,000 roughly. So we compare both systems and look at what we got. We got for a 20-minute window. In that 20-minute window, we got 5 observations with the app for like roughly 30 seconds each observation in terms of time series. And then we compare, this is under ambient vibration, and then we compare with a 20-minute time history or time series record using the traditional sensing. Once we have one observation from the traditional sensing based on 20-minute long time series, and then we got 5 samples with our cell phone, and we got the average of our 5 samples with our cell phone, and we got differences in less or roughly 1%, or even less than 1%. It depends if it's the second, the third, or the fourth natural frequency. Once again, our app and our cell phone, the smartphone, is able to get a very good estimation of the natural frequencies. So we might not say that they have not sensitive to detect the natural frequencies under ambient vibration, as you can see in real world bridges. So, and we also tested our app in order to detect anomalies. Basically, we need to think this is a 2-stage process. The first stage, we need to collect data from our bridges. We need to have a data set with the first 3 natural frequencies from our bridge. And once we have a huge data set, we are able to, at any time, to get a new observation and compare this new observation with the past. That's what we have done. We have done this for both bridges for 1 year. Stage number 1, we collect data for in stage number 1. So as you can see step number one, we need to identify one of the bridge. In this case is the Takayuna's new bridge, because there are two bridges, so the new and the old bridge. And this is the identification. Then step number two, we are collecting acceleration time series, in this case for roughly 20 seconds, it might be 30 seconds. And then we have the feature extraction. We repeat this for 165 times. So we create our data set for 1 year. As you can see here is the bridge, are those two bridges. And you see Yonut here laying down the smartphone and getting the data sets. And here you can see a three-dimensional feature space with the observations composed of the first three natural frequencies for the old bridge in black and for the new bridge in red. So basically each dot is an observation composed of the first, or composed of three natural frequencies. It might be the first, or it might be three that we can just choose between, among several natural frequencies, we can choose three. We just need to choose three natural frequencies. It could be four, it could be five. I mean, we developed, this is a prototype app, so we defined for three, but it's up to you. And once we have our reference data set, let's test it. So once we have those 165 observations, we got a new observation for step number 4. Look at what we got. We got a green dot below the threshold. It says there is no indication of damage. Because of that green dot was below the threshold we defined for the 5% level of significance, we may conclude that the bridge is not damaged, in this case, the new bridge. Of course, I mean, nothing happened in 1 year, so the bridge is in undamaged condition, statistical speaking, of course. And then we tested the robustness of our app. How? So we kept the reference data set from the new bridge, and we tried to get a new observation from the old bridge. And we asked the app, is this observation similar to the ones we collected in the past? And the app says, no, this observation is quite different from the ones we measured in the past. And it gave a red dot, way above the threshold. Of course, we were measuring this new observation in a different bridge, the one that is on the side. But I was trying to show the robustness of our app. Just this is an academic example, of course. Let's move on to another bridge in Portugal. This is Edgar Cardoso Bridge in Figueiredo da Foz, which is the city. This is a cable-stayed bridge which is being retrofitted. So the bridge owner, Infraestruturas Portugal, asked us to get measurements before, during, and after the retrofit. And we used our app. Let's use the app because they wanted to replace those cables. They wanted to replace them. Let's use the app to estimate the internal forces. That's what we try. I will try to show you how we can do that. So this is the bridge, as you can see, and you can see over there. You can see the smartphone tap to the cable in order to get the time series. In closely, you can see Yonut, my colleague Yonut, handling the smartphone to get all the measurements we need. This is an example of step number 1, step number 2, 3, and 4. So basically, you need to identify what is the cable. You get the time series, in this case, for like roughly 40 seconds, 50 seconds. And then you get a power spectrum. Of course, you have many peaks. You need to know in advance. This is a drawback. You need to know in advance which peak do you want, of course. And then you pick those natural frequencies belong to the cable. And then we are able to somehow using a linear equation, we can go from the natural frequencies into the internal forces. And so that's what we did. We estimate the internal forces based on the first 3 natural frequencies. So, and we compare those results to the ones we got in 2021 with the traditional system. So, look, in 2021, with the traditional data acquisition system, we got, using the first three natural frequencies of one of the cables, we got an internal force of 9,000, roughly 9,500 kilonewton. In September 2023, with our app, we did the same and we got 10,000. We have more 5.5% of internal of normal force. And you may ask, oh my God, you have a difference of roughly 5%. But there is a justification for this difference. And we confirm with the traditional system on site. And what happened is this bridge is being retrofitted. So, and they had additional mass caused by those jerseys, those separation barriers. And they had additional mass on the deck, which was causing this incremental axial or normal force in the cables. We got a new measurement in January this year, and the result is pretty much the same. So the force is keeping the same. What is the advantage? The advantage is you just go on site and you hold or you tap or you hold your smartphone into the onto the cable. You wait for 30, 40, 50 seconds. You are able to estimate the internal forces. This is amazing. I mean, from a practical point of view, we are just transposing SHM from the complex orbiter into a very simple reality. So that's the idea that we hope we can develop this app into the future to make SHM available on site for everyone. So just to finalize this app, we are not commercializing the app by now. I mean, we are just developing it for research purposes, but it is available already. Using this link, you can download it directly from the Google Store, Google Play and Apple Store. You can just download it. The app is available for both operating systems. Just to let you know that we have just released the second version, the app for SHM 2.0, which has a better interface. Okay, so this is it. I mean, after this presentation, I'm open to answer. Yeah, Unit and I are open to answer questions. Thank you, Scott.
Thanks, Eloi. All right, I'm going to let Mike switch it back here. So we have, we do have like some papers with the QR code where you can try out the app on the bridge here. We'll do after Mike's presentation. We'll have some time available for that. The apps are free. Roebling Labs has an app as well that has similar capabilities, some differences. But I have tested all the apps on bridges around the Boston area, and it's pretty interesting. If a bridge is very stiff and doesn't have much truck traffic, I wasn't getting consistent readings, but on simply supported, steel bridges, you can get very consistent readings with the app. And I think the real opportunity with the smartphone accelerometers is a crowd sensing model. So setting the phone down on the bridge and taking a vibration reading, it works. But it's not that convenient. It can be convenient, but what the crowd sensing model is, when the smartphone is in a car and travels across the bridge, you get accelerometer data that for one pass across the bridge, that's not that good. But for 100 passes, you start getting quality data, and you can start pulling out damage sensitive features, and it's like you have accelerometers laid across the whole bridge when you start getting that big data. So some of those, who has that accelerometer data? Well, companies, ride sharing companies, the big tech mapping companies, auto insurers do what's called telematics. So if you want to get a lower rate on your car insurance, you might agree to run the app while you drive, like Progressive Car Insurance has that. And then also auto manufacturers like Tesla and self-driving, the vehicles are getting filled with more and more accelerometers. So there is an opportunity to actually use that data for structural health monitoring. And we think that's a big opportunity. And even more so, you don't have to just rely on the natural frequencies, which is very sensitive to temperature. You can rely on mode shapes and changes in mode shapes, which it turns out is not as temperature sensitive, or not really very temperature sensitive at all. So that's sort of a big opportunity for the future. With that, I'm going to turn it over to Mike, who's going to talk about the non-contact sensors, which is it's really a very powerful tool that's used in other industries. I think there's big opportunities for the bridge industry to cross it over into our industry.
Cool. Thanks, Scott. Yeah, my name is Mike Ciocys. I'm with RDI Technologies. We specialize with the motion amplification camera. And so anyone that stopped by our booth this week, we had a couple setups with this bridge, and we were kind of showing what the camera can do just with the pixels that are in the camera and the software that's kind of powering it. The example up here, I have the laptop, I have the camera set up. We're using kind of really standard hardware. There's nothing really special about the hardware. The software is really what makes this very powerful. But when we do motion amplification, we use a camera, and we're using the pixels in the camera essentially as displacement sensors. So every pixel inside the camera we can draw information from. We really kind of talk about the cameras in terms of the resolution. Usually HD is kind of where we start. And HD is 1920 by 1080 pixels. So 1920 by 1080, it gives you 2.3 million pixels to work with. That's in the field of view of the camera. So whatever's in the field of view of the camera is fair game. You can amplify an emotion that's present, and then you can also draw what we call a region of interest, an ROI, on any set of those pixels and extract your vibration data from that. So this ability to draw essentially a box on something that might be very far away, very close up, but non-ferrous, you can't attach a magnet to it. It might be something that you can't reach easily. Really empowers you to put sensors on things in a much easier way without having to actually go out there and do it. So this camera that we're using here has over 2 million pixels in it. And this allows us really to do a qualitative analysis. We can show you with the camera capturing a video what the asset is really doing. And then quantitatively, we draw a box, we extract that vibration information, and I can tell you how much it's actually moving and at what frequencies. My background here, I'm a mechanical engineer. I really specialize with kind of pointing this camera at rotating equipment, pumps, fans, blowers, power generation equipment. That's higher frequency. Bridges are kind of in the lower frequency spectrum. It's really no different. We just kind of run the camera in a different setting. But I like to kind of kick this off. We have an example here. Let me have this restart real fast. It's going to be a pump. It's going to start kind of with a video, and then there'll be this line that goes across. One of the tricky parts about taking videos is that sometimes we're looking at something that doesn't look like it's moving. And so it looks like a static image. In this case, when this video starts, this pump is running. And as the line bar goes across, that's when we're actually showing what it looks like amplified. And so if I start this again, this pump is really running. And then as it goes across, now you can actually see this looseness along the base, and that this pump is actually rocking back and forth. And so it does it again here. That's standard HD video playing at what we would see with our own eye. And then amplified with that line bar to kind of show you here. This will replay a few times so we can see what's going on. But there's this option here to kind of draw that box, and then that's where our vibration data comes from. You can draw it anywhere in this field of view. And so when this changes screen, you'll notice that we drew a couple boxes along the edge of the support here. And then we can turn on this function called vectors that really then takes that vibration data and then kind of animates it. So you get this idea that I might have more direction going up and down, more movement going up and down as opposed to left and right. And that arrow can kind of help you visualize what that looks like. And so you'll see in a couple of videos that we have, those arrows come on, but it's really an animation of the vibration data that we collected at that spot. Excuse me. For videos like this, we don't need to take very long recording. A lot of the recordings of these assets is like 3, 4, 5 seconds. We just need to capture kind of a few cycles of what's happening, and then we can kind of play it back. There's nothing saying you couldn't watch something happening really slow and take a longer video, or doing something that's really, really quick. The trick with our system is that we're taking video that's been uncompressed, unmodified. Our videos are essentially just raw frames of data, which makes them quite large in some ways. And so the only limitation we have in terms of collecting bigger data is just hard drive space. This one will also play on loop. This is 2 of the same video. The one on the bottom is standard HD video, what you see with the human eye. And the video on top is the same thing, but motion amplified. And so in this case, there's this large truck that comes across. If you watch it on the bottom, you don't really see any movement at all. But then when the truck goes across on the top, you see the deflection, kind of undulation of the bridge, just like that. And so qualitatively, this is really kind of powerful to show someone what's going on with the real thing. This is not modeled. It's not like you have to build something in CAD and then apply numerical values to certain areas. This is amplification at all the pixels in the screen. And so if there's things that are not amplified, it's because they're not moving. Only the stuff that's actually moving do we amplify. So that was a bigger bridge. This is, of course, a smaller one. But this kind of really illustrates this idea that we can really draw these regions of interest anywhere in the field of view. And so in this case, we have a blue and a red one kind of drawn on opposite sides of the upper support of this bridge. And we have an out of phase condition. So as this kind of bridge is rocking back and forth side to side, I can take the waveform. In this case, you'll see it's just 5 seconds long. But when I overlay those waveforms, you can actually see this competing forces kind of going back and forth. And so we can visually see that, which is where the amplification becomes really powerful. But we can also take the data and quantify it. There's a lot of circumstances. We have a lot of different users of the system. They seem to fall into 2 different buckets, which is interesting. We have a lot of users that just want to amplify everything, and they want to show it to their boss and say, hey, look what's going on. And then they take action, corrective action normally. And then we have another subset of users that say, I don't want to amplify anything. I just want to draw boxes and collect data all over this scene. There's nothing stopping you from doing both. This would be an example of both. But there's also going to be a lot of videos that you might find on our website or from other users where they don't amplify anything at all. They just want the vibration data. And so they're just drawing boxes and then extracting that information from the recording. This is an example with a grid overlay. This is kind of more of an optical tool just to help the user when they're watching these amplified videos. This will cycle a few times, but it just gives your eye a reference point. And so you can see the behavior after a couple of these trucks and buses go across. But this can just be a real powerful tool to communicate to the team. There's nothing to say that you could take the grid off and leave the grid on. But in a lot of cases, this is really helpful. This is like a 4-second video clip, and you can pretty quickly communicate to someone what's going on. And it's almost one of the largest benefits of the system is you take this data in a really quick fashion. We can then add some annotations or like a grid, make an MP4 out of it, and then you can email this and have someone else looking at this at the same time and being like, is that normal? And then you can say, where do you want to draw some ROIs to collect some data? And then you can start to collect some data and then see quantitatively if you actually have a normal condition or out of tolerance. Here's another example, railroad bridge, but with the vector arrows kind of turned on. And so this kind of bridge starts. There's a lot of like maybe some noise in this one, but you can really sense that you can see in this case the bridge kind of deflecting as the train goes across. But this one's not amplified. So this would be an example of a whole bunch of different ROIs drawn on the scene. You can see from the vector arrows what's going on, but the image was not amplified. So it's really up to the user how they want to kind of portray this. Here's another example. The image on the left is standard HD video, so what you would see with the human eye. and then the image on the right. And this is a tower crane at one of the ports. And so there's some twisting in the structure up top, and then we're also can see some of the movement from as the crane is moving. And then because it's full frame, we can also see some other movement from the different objects in the scene, and that just really kind of shows that you could also extract data from there as well. So this is, I'm showing here kind of the dynamics, deflections, different things reacting as different things are driving over bridges, the rotational speed of that pump affecting the base it's mounted on. We can take this a step further in a different direction and look at what we believe to be static, but maybe it actually has fault. And so this was an example from kind of the rotating asset world, but there's a pump here on the right. You can see this is amplified. So you can see this pipe moving. You can see some movement in the pump down here. They didn't understand what the problem was. They figured it was actually kind of maybe up in the structure supporting the piping. So that's kind of why they were focusing so strongly on this piping, because it was the most obvious thing that was moving. But if I pause it here, the image on the left is HD video, what you see with the human eye, and then the image on the right is amplified. And there's actually a crack in the base of this foundation that becomes really apparent when it's amplified. So you can't see it on the left. You can totally see it on the right. And then when zoomed in, those cracks really, when they're moving like this, really show up quite clearly when amplified. And the fact that this base is so unstable is really then translating through the rest of the system, and everything else is moving because of that. So these are under kind of dynamic situations, usually from some other forcing frequency. The beauty of using a camera is that we can also just watch things plainly move. And in this case, we did some thermal growth studies on the support tower down at Kennedy Space Center. Turns out there's an elevator that runs up and down. Oops, sorry, my mouse on the wrong screen. There's an elevator that runs up and down this 13-story tower, and it trips off sometimes, and then everyone gets upset because they have to take the stairs in Florida in the summer. And so they were curious to know why this was tripping. And so we set up a camera, same system that's out here in front of us, but just off to the side here to kind of capture this. And it turns out in the Florida sun, thought that was going to play in full screen, but we'll run with it this way. This is a place where the grid is really helpful. And this is the top of the tower. And so I'll let this kind of play here. This was taken over the course of a day. And as the sun is hitting the tower, it's actually thermally adjusting the tower, and it's moving by 3 inches at the very top. And so it's you can watch it subtly kind of move. It's when the video loops that you now know where it started and it finished that it becomes really apparent. And so it's actually moving to the right. As it moves to the right, it moves enough that it trips the elevator shaft sensor and it trips the elevator off. And so they're actually, just from the fact that this is standing in the sun, the whole tower kind of just wants to lean to the right. We can better visualize this with another tool, with the vector arrows. So you can kind of see this would be a place where we've kind of drawn ROIs along the kind of almost the last 3 stories of the structure, and then as it kind of moves over to the right. This is a really big thing, moving by quite a lot of displacement. There's also, like, if I come from the rotating world, there's also the ability to see things that are much smaller. And so in this case, this is a hot oil pump that's getting heat soaked before it starts up. And so as the video loops, you see where it kind of like shrinks back to its original size. And so it kind of, but we have some graphs here to kind of illustrate what's exactly happening. So you can actually see quantitatively how much it's growing. But in this case, it's growing only by about 40 to 50 mils and so a really small increment, but it's thermally expanding as it heats up. And so this is a nice place where this is in a motion amplified video, so you can actually see with motion amplification thermal growth or stresses and strains on things. One other benefit of using a camera, I have some equipment up here, is that we can actually do a full modal test. There's a lot of cases where we do bump tests with the camera. We'll use like a piece of wood or a hammer or mallet. And in that case, we hit something, but we don't know the input force. And because we don't know the input force, we can't kind of get some of the other FRF coherence graphs that you can get with modal when you actually know the input. We can partner the camera with some additional hardware and actually use, say, an impact hammer to make some tests. I can also just use the environmental energy. So if you have a truck going over across the bridge, or if you just have wind or something, I can set the software up so I can just use those those kind of input conditions to allow us to do the modal. What's really nice about this, we did some testing on just a metal plate. The system, since it knows all the parameters kind of being entered into the system, can then actually go and find the key frequencies and the mode shapes that are present in that asset. And so in this case, I have 4 different frequencies, and the video is amplified, and the video has been filtered to a band on that frequency. From the graphs you saw on the other slides, I can pick a frequency in that FFT and tell the software to say, hey, filter, in this case, filter at 3.39 hertz, everything north and south of that, take out of the video and make me a new recording, and the system will do that. It's a very common workflow for our users. They'll find something of interest, they'll filter the whole video to it, and you only see what's moving in the video at that frequency. And so this is a really good example, kind of showing that in 4 different ways. In the top left at 3.39 hertz, you get this kind of rocking, kind of back and forth. A little bit higher in the frequency range, 17.4 is actually kind of more of this twisting, a little bit of a torque in there. At 23, it's kind of this back and forth motion, kind of in and out of the screen. And then at 50 hertz, you get this kind of deflection, kind of upon the middle axis. And all of this was taken from the same raw data. It's just been filtered 4 different times against 4 different mode shapes that the system detected. That's more of a testing scenario, but like, what if we had an actual kind of system in place? How could you actually use this? This is a set of pumps, hydraulic pumps. Same equipment was used, except the impact was made up in the top left on the piping. And then the whole scene here was recorded with the camera to measure the response. In this case, there was a 12.86 hertz frequency that showed up in the data. We filtered the whole video to that frequency. We had to amplify it a lot, 160 times. So this is not something of high amplitude, but it is something that's there. And so this is something that's very, very subtle. But amplified at that level, you can see there's actually this 12.86 is the movement of the pipes kind of out of phase on an as-is kind of installation. This is really powerful because in the factory, these might be tested to make sure they're not going to maybe excite something at this frequency. Once they get installed, you still need to verify that the installation condition is not going to present something that then excites that frequency. So in the bridge world, I'm happy kind of partnering with Scott with this, and he brought me out. This is my first time at the show, so I'm happy to be here to kind of talk about this and how this might be used in the bridge industry. We talked about thermal growth, crack detection. I think that'd be really powerful. That's some of the stuff we've also seen with some of our service team. Deflection, strain, measuring deflection of the different key components. A lot of commissioning. Kind of to my point with the pumps is that in a design situation, are you getting that in actual reality when it's actually installed? We have a couple cameras here. In terms of how they're kind of deployed. This one's got on the tripod with a laptop, can be moved around. But there's also an openness that we have other cameras that could be more permanently installed and watch something for a much longer period of time. In that case, you could actually, we swapped the laptop for an industrial PC, and then you could watch something for months or years. Scott, I'm going to hand it back to you here to kind of close up our section on this.
Yeah, just to wrap up the sort of panel presentation part of this, our theme is how might these tools help you better manage your bridges? And for both the non-contact sensors and the smartphone accelerometers, we're really, we're seeking partners to do pilot projects or case studies and really see how we can integrate these technologies into the bridge industry. With that, we have some papers with the QR codes if you want to download the apps and try them out. We invite you to come up. Also, if anybody has any questions right now that they want the whole group to hear, we're happy to take questions. Otherwise, yeah. I couldn't.
Sorry.
I don't think we heard the question. Could you bring Eloi up on the screen? And I'm gonna repeat your question. I think your question's for the professors in Portugal mostly, so I'm gonna he'll bring him up on the screen and I'll repeat the question so he can hear it. You're asking if the phone app has ever been used in a seismic situation and how it performs with higher frequencies. I'll let Eloi respond, but the smartphone apps go up to about 25 hertz frequency.
Yeah, can you hear me?
Yeah.
So during the developing of the app, we realized that we could not go further in terms of sampling frequency than 100 hertz. So that's why we kept by default for 50 hertz. It means that we only have frequency content until 25 hertz. And the app hasn't been tested under seismic excitation yet. So we have just used the app for bridge situations under ambient vibration. That's basically what we have done.
All right. Why don't we can take a break, and anybody that's interested, feel free to come up. You can play with the camera, play with the smartphone apps. We have a model bridge up here, and we're happy to chat, answer any questions, and so forth. Thanks for coming.
Thank you.
Do some technical swap. Eloi, thank you very much.
Thank you, Mike, and thank you, Scott. And I'll be here, Scott and Mike.
Yeah, you can. Yeah, you can stay here. I'll keep you on the laptop if people have questions.
Okay. Okay. Thank you.